Okay, what's this say?
Grams.
Gram? Grams of KNO3, is that what you're after?
Yes.
Mm-hmm. And then if you start with the molarity of the solution, 0.05 moles for every liter, moles on top, liters underneath.
Then, hold on. The third. So you change it from liters.
They change it from moles to liters.
Molarity is moles per liter, and then you can get rid of the liters on the bottom with the 25.33 or the 0.02533 liters. Good. So now you're in moles of KNO3, right?
Yeah.
And you need to get to grams of KNO3. So moles of KNO3 are going to go down here to get rid of them. Then you're going to go to grams of KNO3. So you got moles per liter. Good. That's how many liters of solution. And you don't need that moles in there. You don't always need to have something in the top or the bottom, right? But now you need to convert this moles of KNO3 to grams of KNO3. Good. That's how many grams of KNO3 there are for every 1 mole of this stuff, right?
So you said this doesn't have to be there?
Yeah, that doesn't go there. I mean, you don't have to have something in the top or the bottom. So you went from grams to moles. Oh, sorry.
Yeah.
Moles per liter. Got rid of liters. Now this is, what is this?
Starting with the moles again?
No, you don't need to have something there. So people are getting antsy that we don't have something in the top and the bottom, right? It's okay. You don't need to have something in the top and the bottom because you've started with kind of a fraction and you just need to get rid of units. Now, if we've gotten rid of these two, we're in moles, and you just go from moles to grams
Okay.
because we want grams on top, right? So you don't need something here, right? There's nothing there. That's where the 0.05 is there. Oh, not there. That one's right. But not on the bottom. You don't need something on the bottom. Does that make sense? So now you got 0.05 moles for every liter. And this got rid of your liters of solution. So you're in moles. And now you're going to go from moles to gram. Because this one is 101 moles. Or not 101. 1 mole is 101 grams.
These are just swap.
Hmm?
It's just swap.
Yeah, but this shouldn't say grams per mole, right? It should be grams per mole, but you're right that they have to be swapped because you need to get rid of moles there. Does that make sense? You got?
At first I put the mold there and then,
Yeah,
oh sorry, I have this.
you're correct that it doesn't go here, but it doesn't go here either because you're in moles of KNO3 now and you want to get to grams of KNO3.
Oh, so it goes down.
Yeah.
Oh, yeah.
Did you get it okay?
That.
Oh, okay. This is moles of KNO3.
Yeah.
So here you've multiplied by moles again. That would be moles squared per gram.
Okay.
You need to swap those two, right? Yeah, good. You need grams of KNO3 up here. And what units do you need down here?
Is it?
What? Yeah, because you need to get rid of those moles. Okay. Did you figure it out?
Yeah. I got 0.128 grams.
0.128? Does anybody else get 0.128? Okay, let's take a look. Okay, so we have moles of solution per liter, or moles of solute per liter of solution. This is how many liters of solution. That got rid of those liters of solution. Now I'm in moles of KNO3, right? So you have to, after you add in some sort of a conversion factor or put a value here, look at your units and see where you're at. In this case, we need to get rid of moles of KNO3. And we need to convert that to grams of KNO3. And we know that there's 101 grams for every mole. That's this here, all right? Okay. Very good. So, all right. Let's talk about the day you went to the party and the juice was too sweet. Do you guys remember that day? That was a pretty bad day, right? However, you being a chemist were quick to recognize what needed to be done. Right? You had this red punch. It was so strong, you're like, how am I going to enjoy this party? The punch is horrible. But you knew if it was half as sweet, you'd be okay. Right? So let's give some values here. Let's say that this was 100 milliliters of solution, and let's say it was 4 molar. All right? And what concentration do we want it at? Not 4 molar. What do we want it? 2 molar. We said we want it half as sweet. So we're going to need a bigger cup, right? Why do we need a bigger cup? Yeah, we're going to be adding water to it, right? If this is our 100 milliliters of punch, how much water are we going to add? Another 100 milliliters. And so the volume is now going to be up here. And the punch is going to be, there's going to be 200 milliliters of it. And it's going to be less concentrated, right? What is the new concentration going to be? 2 molar, the new concentration. All right? This is just a snapshot of your memory. All right? This is just a picture from your memory. Remember the good old days when that happened, right? So this is the picture frame. You can think of it in your memory. All right? This is just something that you're going to be able to draw on anytime you're in the chemistry lab and you have to perform a dilution of some sort. You can take information like these, and you don't have to remember the 100 and the 4 and the 200 and the 2. Just some numbers, you make them up. You remember the time you did this? Yeah. And then you remember that this represents the initial volume. This represents the initial volume. And this represents the initial concentration, whereas this one here is the final volume, and this one is the final concentration, right? And knowing that those are the values that you've chosen for your memory, you can think about what the relationship is, because there is a relationship. And you can use the dilution equation. You can go and put some values in and see what the resulting equation is. But this is what it is. It's the concentration initial times the volume initial will equal the concentration final times the volume final. All right? So, if we're asked to perform a dilution like this one, we need to create 250 milliliters of a 3.2 molar solution from a stock of 12.1 molar. Where would my 250 go? What's my 250 on here? Initial what? What's that? Is it the initial volume or the final volume? Yeah, that's how much we want at the end. So the 250 will go here. What's the final concentration? Do we know? We want the stuff to be what? 3.2. Okay? Do we know our initial concentration? 12.1. Do we know how much of our initial volume material we need? We don't, but we can solve for that. Right? So we identify how much of the 12.1 solution we need by doing this. And we put that in there. The answer is 66. The units for the 250 here was in milliliters. So this is units in milliliters. All right? So that's how we perform or utilize the dilution equation to answer questions about making solutions or what the concentration is after we do a dilution. So here's one. We got some initial volume, initial concentration. We dilute it to a final volume, and we want to solve the final concentration. Can you find out what the final molarity is for this problem here? This is pretty easy, right? The only thing hard about this is 1 remembering this equation, which you can remember just by thinking of any scenario and then finding out how they relate to each other. And 2, understanding what they're asking. Are they asking for the final volume? Are they asking for the final concentration? Are they asking for how much water needs to be added? Because that's not one of these values, but it can be determined from it, right? So what'd you get? What is the molarity of the resulting solution? 0.3 molar? Who got that? Anybody want to go over that one? Okay. So we looked for the dilution equation, C1V1 equals C2V2, or C final V final. The initial concentration was what? 6 molar. It says we took 25 milliliters of this 6 molar solution, right? And we diluted it to 500 milliliters. 500 milliliters, what's that? Is that the final concentration or the final volume? Volume. 500 milliliters is the final volume. So then if we solve for that x, that should be our final concentration. Does that make sense? All right, excellent. Here's a tricky one. Let's see if you can do this one now. This is the other hard part. Not just remembering the equation, but then answering the question that they actually ask. See if you can get this one right. What's the initial concentration? 3.11. What's the initial volume? Looks like we took 20 milliliters of it, right? Okay, did somebody get an answer? B as in boy? Anybody not get B? Raise your hand if you didn't get B. Raise your hand if you got B. Still not terribly convincing. Okay, so our initial concentration was 3.11. And they're asking what the final concentration is? And we said it was 4.15, is that right? Does the concentration go up when we add water? So we're taking this stuff and we add water and it goes up to 4.15? Does that make sense or no? What happened? What happened? Did they say the final volume was 15 milliliters? What's the final volume? It's 35, isn't it? What's the 15 milliliters then? What's that stuff? That's what they added. Okay, so they added 15 milliliters to our 20, so the final volume is 35. If we use the 35 in there, what do we get? Is it 1.77? Okay. Everybody see where we got the 35 from? Yeah? Where did we get it? Why did we add them this time? We didn't do that before. Yeah, because it says not the final volume was. It says if you add this much water, what's the final concentration? Right? Okay, very good. Now, a titration. A titration is a kind of experiment that you can perform in which you have a known concentration of one thing and you mix it with an unknown of some other thing. Here I have some sodium bicarbonate. Sodium bicarbonate. Okay? And if I put a little bit of sodium bicarbonate into here, there we go. A little bit into there. Oops, this has some stuff in it already. And then here I have an empty one. I'm just going to put some water into here. Let's see. Let me go outside for a second. Don't look, don't look. It's magic. Okay, try again. Here I have my sodium bicarbonate, or sodium carbonate. I'm going to put a little bit in here. There we go. And then I'm going to add some water. All right, so now I've made a solution of my sodium bicarbonate, or sodium carbonate. Okay, there it is. I'll put a stir bar in there, and then I'll put it over this stir plate. Oh, the stir bar's got stuff on it too. And I'll turn the stir bar around. In this one here, I'll just put water. Okay? And I have, in a titration reaction, what's called an indicator. This indicator is colorless if the solution is acidic or neutral, like this one. But for this one, where it's basic, it turns it color, it turns the indicator, the basicity turns the indicator a pink color. Okay? In my burette here, right, and you guys are all really good at measuring values on burettes now, right? This starts at 0 and counts up, down. As you move down, it counts up to 50. So the reason it does that is because you could get an initial measurement and then deliver some and then stop and find out how much you've delivered by taking the final minus the initial. Okay? So my burette here has an acid in it. An acid in it, like this. It's HCl. And I'm going to deliver HCl into my solution of sodium carbonate, right? And I'm going to find out how much sodium carbonate there is in that little container, what the mass of the sodium carbonate is, right? Because as soon as the sodium carbonate runs out, right, the solution will turn colorless because extra acid will have been added, and that will cause this pH to go low. Is this hot? Whoops. Don't want this hot. I got the heat on there. Oh, off. There we go. Okay. All right. So now I've added enough acid that it's what? Goes clear, and my indicator turns clear. Now if I add some more of my base, right, then it should do what? Should turn pink again, because now there's base in there. So would somebody like to come up, and who said the prayer? You said the prayer, right? You want to come up? Give it a shot? Not really? You could pass it on if you don't want to. But what we want to do here is we want to measure the volume of HCl required to turn it just barely colorless. We don't want to go too much, because if you go too much, then you're adding extra. So you can go fast by going like this, really fast, and you can go slow as you want.
So what do I do?
You want to keep adding it until all the pink goes away. But you don't want to do any extra. You want to try to make it so it's just barely gone away.
That can take a long time. Right?
Maybe, yeah. So you could go faster if you wanted to. Whoa, slow down. Man, who knows?
I messed it up.
So,
Sorry.
now we would measure this, and we would see, oh, she's delivered 25 milliliters. We knew the concentration of the acid. We made the acid. It was 3.11 molar. All right? And now we can know what mass of sodium carbonate I had added in there. All right? So that's a titration, an example of a titration. So when they talk about titrations, you'll be familiar with it. So what mass of sodium carbonate was in there? When I was putting the mass of sodium carbonate, what mass was in there if it required 25 milliliters of 3.11 molar HCl to titrate it. Equal sign, units that we're after, start with molarity or the volume, right? Now this one is going to be a little more tricky because we need to know the stoichiometric relationship. We need to know the equation for how these two react together. What goes to the right of the equal sign? Grams of sodium carbonate. What are we going to start with over here? .11. Man, is that still heating? 3.11 moles of, was that my computer? Anybody know what that was?
I think there was one.
Okay, because we heard that last time, I thought, or maybe that was something else. HCl for every 1 liter of solution. How did I know this business? What is this? Moles per liter? This is the what? What do you call this? Molarity. The molarity. Right. How do I get rid of liters of solution? 0.025 liters of this solution, right? Of my HCl solution. Now I'm in moles of HCl. Does everybody see how I did that? And we want to go, we don't want to be in moles of HCl, do we? And we don't want to be in grams of HCl. We want to be in grams of sodium carbonate. How are we going to get there? Is there any hope for us? The land of the moles. There might be something valuable there. What's in the land of the moles that we might be able to take advantage of? The stoichiometry of the equation. That's right. So if we go for moles of HCl, we might be able to identify what? Moles of Na2CO3. Okay, let's see. What happens when I mix HCl with Na2CO3? What's the products? Very good. Hydrogen with the carbonate ion. What's the ratio there? Is it 1 hydrogen or 2? What's the charge on the carbonate ion? What's the charge on the hydrogen? +1. What's the carbonate ion? What did we say? -2. So I need 2 hydrogens, don't I? Okay, what's the other product? NaCl, I think I heard it. Right? NaCl. Now, the power of the equation won't help us if the equation is not balanced, will it? Is this equation balanced? What do I need to do to balance it? A 2 here? A 2 here? Okay, it's balanced now. So we went to the land of the moles. We have access to the power of the stoichiometry, right? And that's here. 2 moles of sodium chloride or hydrochloric acid for every 1 mole of sodium carbonate. And now that I'm in moles of sodium carbonate, what do I have to go to? Grams of sodium carbonate. Very good. Moles of sodium carbonate to grams. And that's still 106. It's up there. Okay, is the answer here?
Yeah, how did you get the 2 moles of HCl?
Why did I know this had to be a 2?
No.
This is where I got that. It's 2 moles of this for every 1 mole of that.
Oh.
And how did I know that this had to be a 2? I had to balance the equation, right? Is one of the answers up there? What is it? 4.12 grams. So we had the mass of sodium carbonate in there. I knew the concentration of the HCl. I titrated it. We delivered 25 mils. And so I could identify how many grams of sodium carbonate were in that sample. Okay? Let's see if we can do one more before you guys leave. Here it is. 25 milliliters of HCl is titrated with 75 milliliters of 1.3 molar calcium hydroxide. What is the concentration of the HCl? This one is going to be a Halloween problem. Okay? What units go to the right? What are we looking for to the right of the equal sign? Very good. Moles of what? HCl for every 1 liter of solution. Is that true? Yeah, they're asking what's the concentration of the HCl. There it is, concentration, moles per liter. What are we going to start with? The top left here. 1.3. Now, I don't want to write molar, right? I want moles for every liter of this material. What is this stuff? It's calcium hydroxide for every liter of solution. Right? What can I do next? All right, 0.075 liters of the, I'll write in here to make sure everybody can see where we got it, the calcium hydroxide solution. So now I got rid of liters of solution, right? Now what do I got to get rid of? Moles of calcium hydroxide, right? Where's it going to go? What are we going to try to get to it from there? That's right, moles of HCl. Can I relate those two together? I can through the land of the moles, power of the equation, stoichiometry there, right? So what happens when I mix HCl with calcium hydroxide? What are the products? Calcium chloride? Is that how you make calcium chloride? Good enough. Does it matter if I know how? It doesn't matter. We can just vote, right? We can all agree. It's okay. No, you need to make sure that you recognize that chloride's a +1 or -1 and calcium's a +2. You need the right values there so that you can get the right stoichiometry. Okay, so what's the other product? Water, H2O. Do I have to balance it? Yeah, I need to have it balanced, so I'm going to use the stoichiometry. What's the answers here? I need a 2 here. I'm going to get a 2 here. Very good. So what that does for me is tells me that there's 2 moles of this for every 1 mole of that. I got moles of HCl on top. I'm really close now. What do I got to get down here? Liters. How many liters of the HCl solution did we have? 0.25 liters of the HCl solution. Okay, that should be it. Anybody do it? Anybody get a value? What value is it? 7.8. That's the molarity of the HCl. Good. 7.8. 7.8 molar HCl. That's our answer. Okay. Very good. We're getting to a point where we can answer questions that we didn't know we could answer, right? Just trying to manipulate the units. Shouldn't we just leave that up there? It just looks so good.